In this video lecture, we will study about Newton's third law. So the definition: for every action there is equal and opposite reaction. I believe every one of your students have used this statement in Facebook or in your chatting, that for every action there is an equal and opposite reaction. We use this sentence in our daily conversation, so we know what that means. Okay, now in this lecture we will try to look more deeper, like how that statement came into effect, why it is true, why it is so important to understand our daily life. Things are happening in our surrounding areas, why they happen. One example, let's say there is a box on a table. So this is a big table. I have multiple boxes on the table. Box 1, box 2. Okay, so we know as this box is on the table, the box is applying some force because of the weight of the box. There is some force acting on the table in a downward direction. We know that. One thing which is interesting, which would be probably new for some of the students, and some may already know, that as the box is applying the force, the table is also applying the force in the opposite direction. Let's say F2, this was F1. The force F1 and F2 is going to be equal in magnitude and opposite in direction. Okay, so whenever there is an interaction, so there is an interaction here, right? This interaction between the box and the table. Whenever there is an interaction, there would be a force, and those forces will always occur in pair and in opposite direction. Those are called action and reaction force. Okay, so as this box is applying the force on the table, you can think of that as an action force, and the table is applying F2 to counter that. That would be a reaction force. So whenever there is an interaction, we have learned this before in our force lecture, that whenever there is an interaction, there would be a force, and those forces would be always coming in pairs. That is action and reaction. Those would be equal in magnitude and opposite in direction. Similarly, now for this box, this would be applying another, let's say F3 on the table, and the table would be applying F4. Those would counter each other, and since this box is not moving, is a zero velocity, so velocity is zero. That's why those F3 and F4 are, because they are balanced forces. Okay, let's look at some more example here. This person is applying some force on the car, right, to push it forward. So person is applying the force F. Now car will also apply another force, F dash. Okay, let's call it F dash, and those F and F dash would be equal in magnitude and opposite in direction. As this person is lifting the rock is applying some force because of the weight of the rock, let's say F, and this person is applying the force F dash. Keep it steady. So as you can see, there are action and reaction. What's happening in this one? Same thing, there is an interaction here. So rock is applying the force F down, the person is applying the force F dash up, and F dash are same. This person is hammering the nail, so nail is applying the force F1, the hammer is applying the force F dash. So we see this examples of Newton's third law everywhere. For every action there is equal and opposite reaction. Okay, now there was one very big misconception, or probably a very interesting thought, which we will try to solve to understand this law more. One of my student was asking me, like, I play basketball, okay, and you said for every action there is equal and opposite reaction. So as I'm like bouncing the basketball, right, and then applying so ball is touching the earth, so there is a contact here. So ball, once it touches the earth, like the earth will apply the force in upward direction, let's say F2, and ball will apply the force in downward direction, let's say F1. So after the ball touches the earth, my ball bounces back, but earth doesn't bounce back. Why is that? But you said for every action equal and opposite reaction. So if my ball is bouncing back, so if this is the ball, as it is coming, it's bouncing back. why the earth is not bouncing back, why the earth is not going downward. Very good, very good question, and very important question to understand this more. Okay, so means one thing which is clear from the Newton's third law, as this ball is coming and touching the earth, it's applying some force in the downward direction, right? F, and the F1, and then earth is applying the force F2. We know from Newton F1 magnitude wise is the same as F2. Okay, that is true. So let's say the mass of this ball is m1 and acceleration is a1. Earth, let's say, is m2 and acceleration is a2. So we know force is what? Mass into acceleration. So this equation we can write as m1 a1 is equal to m2 a2. Okay, so let's say the mass of the ball is about 1 kilogram. That is actually pretty heavy. Generally it is less than that. And what is the mass of earth? That would be a good question, right? So the mass of earth is pretty huge. We know that it's 5.9 something into 10 to power 24 kg. It's huge, right? And let's say that as the ball is bouncing back, the acceleration is 10 meter per second square. So if I put that 1 kg times 10 meter per second square is equal to 5.9 into 10 to power 24 kg into A2. Okay, now what is this value? So if you calculate the value of A2 from this equation, the A2 would be is basically pretty small. It's 1.7 into 10 to power minus 24 meter per second square. This value 10 to power minus 24 is pretty much zero. It's hardly any change. So the initial question, whether the earth will move with some acceleration, answer is yes. There would be some movement of the earth, but the value is hardly anything. It's practically zero compared to the 10 meter per second square of the ball. That's why you see the ball bouncing back with some acceleration, but earth did not, because there is hardly any movement in the earth. Okay, I hope that makes things clear. So remember, for Newton's law, whenever there is a contact, which is something like this, there would be, or there is an interaction, there would be pair of forces, and those pair of forces would be equal in magnitude and opposite in direction.